Hello, all. Today we will discuss about language evaluation criteria, and this subject mainly focuses on concepts of various constructs and capabilities of language, different programming languages, and we need to evaluate these features of these languages, focusing on their impact on the software development process and also the maintenance. So for performing this evaluation of these features of programming languages, we are setting some evaluation criteria. And we know that if we give a list of criteria for this evaluation, that may be somewhat controversial, because if we have two computer scientists, it is very difficult that they will agree on the value of some given language characteristics relative to others. Okay, even though we have some differences, we have these kind of language evaluation criteria, and there the first uh, criteria is readability, and under readability we have writability, then overall simplicity, orthogonality, data types, and syntax design. And we have writability, their simplicity, orthogonality, support for abstraction, expressivity. And we have reliability, that is type checking, exception handling, aliasing, readability, and writability, then cost. And here some of these characteristics are very broad and somewhat vague. For example, writability. But other characteristics are very specific language constructs, such as exception handling. Okay. So we'll give equal importance for all these criteria. And let's see language evaluation criteria. Let's see one language evaluation criteria and the characteristics that affect them. So the criteria: readability, writability, and reliability. And we have a situation. These are the characteristics, that is simplicity, and there we have readability, writability, and reliability. And we have orthogonality. All these three criteria will be evaluated for getting the orthogonality. Data types, syntax design for all this, and for support for abstraction we need to evaluate only this writability and readability, etc. And for type checking we need to evaluate this reliability. Okay. So let's see first we'll see readability. So one of the most important criteria for judging a programming language is the ease with which programs can be read and understood. That is, before some early 70s, software development was largely thought of in terms of writing code. So what we mean by software development is that we are writing codes. So the primary positive characteristic of programming languages was efficiency. So language constructs were designed more from the point of view of the computer than of the computer users. So because we need to focus on the efficiency, so these language constructs, different languages have different constructs, and these were designed from the point of view of the computer rather than the computer users. And in 1970s, the software life cycle concept was developed. Okay, and coding was relegated to a much smaller role, and maintenance was recognized as a major part of the cycle in terms of this cost. And because ease of maintenance is determined in large part by the readability of programs, the readability became an important measure of the quality of programs and programming languages. So we have, after this 1970s, we have the software life cycle concept, and there we have coding has a very smaller role, but maintenance has got a major part of the cycle. and our aim was to ease this maintenance. So because ease of maintenance is determined large part by ease of maintenance. If the code is readable, then it is easy to maintain that code. Okay, so ease of maintenance is determined in large part by the readability of programs. Readability became an important measure of the quality of programs and programming languages. That's how this readability came into picture. And this was an important point in the evaluation of programming languages. And we have a distinct crossover from a focus on machine orientation to a focus on human orientation. And as we know, the readability must be considered in the context of the problem domain. For example, if a program that describes a computation is written in a language not designed for such use, the program may be unnatural and convoluted, making it unusually difficult to read. Okay, so that's what we say. Depending upon the problem domain, we need to fix the type of language, the programming language. Okay, so if it is used for computations, then it must be used or we must use a language that is designed for computation purpose. Otherwise it makes the program will become very difficult to read. Okay, and this the next subsections describe the characteristics that contribute to the readability of this programming language. And the first subsection is about overall simplicity. And the overall simplicity of a programming language strongly affects its readability. So what we usually know is, or what we usually tell is, we should write the code in a very simple manner. Okay, so the overall simplicity of a programming language affects its readability. If it is very simple, that is easier to read. Okay, and a language with a large number of basic constructs is more difficult to learn than one with a smaller number. So if we have a large or enormous number of basic constructs, and those kind of languages or those programs written in those languages are more difficult to learn than one with a smaller number. Programmers who must use a large language often learn a subset of the language and ignore its other features. Okay, so that is very important. So programmers who must use a large language often learn a subset of the language. So if we need some part, if we want to use pointers, we'll study about pointers. Okay, and sometimes we'll ignore its other features. Okay, this learning pattern is sometimes used to excuse the large number of language constructs, but that argument is actually not very valid. Readability problems occur whenever the program's author has learned a different subset from that subset with which the reader is familiar. Okay, so that's the readability problem occur whenever the program's author has learned a different subset. Because what we say is that suppose we have a program and we are trying to read this program, but for example that is written using, or that is for performing some file operations, for example. Okay, but we haven't studied or we haven't looked at this file concepts in C language. For example, we are talking about C language. Then what will happen? Because most of the programmers will stick on the language constructs which are useful for them only. They will ignore the other portions. So if we have a program which is written for file operations, for performing these file operations, then it is very difficult for this kind of learner or this kind of programmer. So, and the second complicating characteristic of a programming language is feature multiplicity. Okay, feature multiplicity means having more than one way to accomplish a particular operation. Okay, so other characteristic of a programming language, complicating characteristic is feature multiplicity. That is, for example, for performing a particular operation, we have different ways, more than one ways. Okay, For example, in Java, a user can increment a simple integer variable in 4 different ways. For example, the variable name is count, then we can use count is equal to count plus 1, or count plus equal to 1, or count plus plus, or plus plus count. All these are for incrementing a simple integer variable. Okay. And we know count plus plus and plus plus count. These two statements have slightly different meanings from and from the others in some contexts. All of them have same meaning when used as a standalone expression, that is used to increment a value of a variable. And a third potential problem is operator overloading, in which, and operator overloading means we have a single operator symbol and this has more than one meaning. And we know this operator overloading is often very useful. It can lead to reduced readability. The case is if users are allowed to create their own overloading and do not do it sensibly. Okay, we have the option of operator overloading, so users will keep on overloading the operators and do not do it sensibly. Okay, for example, it is acceptable to overload this plus to use it for both integer and floating point addition. This overloading simplifies a language by reducing the number of operators. However, suppose the programmer defined plus used between single dimensional array operands to mean the sum of all elements of both arrays. Okay. So suppose we define a plus used between a single dimensional array operands, that is to mean the sum of all elements of both arrays. That is the meaning of this plus. Because the usual meaning of vector addition is quite different from this, it would make the program more confusing for both the author and the program's readers. An even more extreme example of program confusion would be a user defining plus between two vector operands to mean the difference between their respective first elements. Okay, suppose we are using this plus for vectors alone, but that is for finding out difference between their respective first elements. All this will make some complications. And simplicity in languages can be carried out too far. For example, the form and meaning of most assembly language statements are models of simplicity. As you can see, when you consider the statements that appear for the following example. So this is simplicity, however, makes assembly language programs less readable. So what we say is simplicity can be carried too far. That is, the form and meaning of most assembly language statements are actually models of the simplicity. As you can see when you consider the statements that appear in the next section. So this very simplicity makes assembly language programs less readable because they lack more complex control statements. Program structure is less obvious because the statements are simple. Far more of them are required than in equivalent programs in a high level language. Okay. So that is about this overall simplicity. And the second thing is about orthogonality. So orthogonality in a programming language means that a relatively small set of primitive constructs can be combined in a relatively small number of ways to build the control and data structures of the language. Okay. Orthogonality means in a programming language means a relatively small set of primitive constructs. So we have a small set of primitive constructs and these can be combined in a relatively small number of ways to build the control and data structures of the language. Okay, so we have primitive constructs. By using that, some mix and match, we build the control and data structures of the language. Every possible combination of primitives is legal and meaningful. For example, consider data types. Okay, so suppose a language has 4 primitive data types. and for example integer, float, double and character. What happens? And two type operators, array and pointers. If the two type operators can be applied to themselves and the four primitive data types, a large number of data structures can be used. So we have some derived data types like this. We have some primitive data types and we derive, or we use some mix and match and will build some derived data types. And the meaning of an orthogonal language feature is independent of the context of its appearance in a program. And the word we have orthogonality, the word orthogonal comes from the mathematical concept of orthogonal vectors, which means that these vectors are independent of each other. That's what we say. Orthogonal language feature is independent of the context of its appearance. So if we are using an orthogonal language feature in some context, that is independent of this particular context of its appearance in a program. That's what that is equivalent to orthogonal vectors. And orthogonality follows from a symmetry of relationships among primitives. And a lack of orthogonality leads to exceptions to the rules of the language. And in a programming language that supports pointers, it should be possible to define a pointer to point to any specific type defined in the language. Okay. If pointers are not allowed to point to arrays, many potentially useful user-defined data structures cannot be defined. That's what we say. Programming language that support pointers, it should be possible to define pointers to point to any specific type defined in the language. Okay, that is not particular to some types. Okay. And this orthogonality is simply is closely related to simplicity. So the more orthogonal the design of a language, the fewer exceptions the language rules require. Fewer exceptions means a higher degree of regularity in the design, which makes the language easier to learn, read and understand. So anyone who has learned a significant part of the English language can testify to the difficulty of learning its many rule exceptions. So as an example of the lack of orthogonality in a high level language, suppose consider the following rules and exceptions in C. And we know, as although C has two kinds of structured data types, that is arrays and records, structs. Okay. Records can be returned from functions, but arrays cannot. A member of a structure can be any data type except void or a structure of the same type. An array element can be any data type except void or a function. And parameters are passed by value unless they are arrays, in which case they are passed by reference. If it is an array, those will be passed by reference. Okay. And so as an example of context independence, suppose we have a C expression like A plus B. And this expression means that the values of A and B are fetched and added together. A plus B. If A happens to be a pointer, it affects the value of B. Okay. So for example, if A points to a float value that occupies 4 bytes, then the value of B must be scaled because we have addition. Okay. In this case, multiplied by 4 before it is added to A. Therefore, the type of A affects the treatment of the value of B. So that is the context of B affects its meaning. Okay. So the third point is data types, and we know about the data types. So the presence of adequate facilities for defining data types and data structures in a language is another significant aid to readability. For example, suppose a numeric type is used for an indicator flag because there is no Boolean type in the language. In such a language, what we will do, we might have assignments such as the following: timeout equal to 1. So what we do is we have an indicator flag. Usually the flags will have Boolean values, but we have a mechanism, or we are using a numeric type for this indicator flag, because the language doesn't support this a Boolean type. Okay. So therefore, what we can do, the indicator flag will be set something like timeout is equal to 1, and meaning of the statement is unclear. Whereas in a language that includes Boolean types, we would have the following, that is a timeout is equal to true. That is, instead of this 1, we have timeout is equal to true. So meaning of this statement is perfectly clear in that sense. Okay. And the fourth point is about syntax design. The syntax means the form of the elements of language has a significant effect on the readability of programs. So for example, let's consider some cases, that is special words. The first example is about special words. Program appearance and thus program readability are strongly influenced by the forms of a language special words. For example, while, class, for. So especially important is the method of forming compound statements or statement groups, sorry, primarily in control constructs. Some languages have used matching pairs of special words or symbols to form these groups. Okay. C and its descendants use braces to specify compound statements, that we know. All of these languages suffer because statement groups are always terminated in the same way, which makes it difficult to determine which group is being entered when an end or a right brace appears. Okay, so that is the case where we have a problem with this kind of special words. Okay, so we have an end or we have a right brace appears, but we know most of the statement groups are terminated in the same way. So when we see a right brace or end statement, it is not clear that which statement has ended. Okay. Fortran 95 and ADA make this clearer by using a distinct closing syntax for each type of statement group. For example, ADA uses end if. Okay, that is to denote end of this if statement. Okay, and end loop to terminate a loop construct. Okay, and this is an example of the conflict between simplicity that results in fewer reserved words, as in C++, and the greater readability that can result from using more reserved words, as in ADA. And another important issue is whether the special words of a language can be used as names for program variables. That we know, we have, each language has some reserved words and that cannot be used as variable names or program variables. If so, the resulting programs can be very confusing. For example, in Fortran 95, special words such as do and end are legal variable names. Okay, so in Fortran 95 language. So the appearance of these words in a program may or may not connote something special. And second example is form and meaning. So designing statements so that their appearance at least partially indicates their purpose is an obvious aid to readability. So the main problem is we have some set of statements and we cannot understand its purpose. Okay, so we need to design the programming language designers must design statements so that their appearance partially indicates their purpose in an obvious aid to readability. So semantics or meaning should follow directly from syntax or form. Okay, so when we have a syntax, the semantics should also be there. In some cases, this principle is violated by two language constructs. that are identical or similar in appearance but have different meanings depending perhaps on context. For example, in C language, the meaning of the reserved word static. Okay. For example, the word static that depends on the context of its appearance. If used on the definition of a variable inside a function, it means the variable is created at compile time. Okay, if used on the definition of a variable that is outside all functions, what is its meaning? It means the variable is visible only in the file in which its definition appears. That is, it is not exported from that file. Okay. So we have special syntax design is a major concern, and the second evaluation criteria is writability. So writability is a measure of how easily a language can be used to create programs for a chosen problem domain. So we know we have a problem domain, so depending on that we select or choose the language. Okay, so most of the language characteristics that affect readability also affect writability. Okay, so this follows directly from the fact that the process of writing a program requires the programmer frequently to reread the part of the program that is already written. Okay, so if the writability is compromised, then the programmer has to read the part of the program. As is the case with the readability, writability must be considered in the context of the target problem domain of a language. It is simply not reasonable to compare the writability of two languages in the realm of a particular application when one was designed for that application and the other was not. For example, the writabilities of Visual Basic and C are dramatically different for creating a program that has a graphical user interface for which VB is, that is Visual Basic is ideal. Okay, so depending on the problem domain, we can fix the languages. So their writabilities are also quite different for writing systems programs such as an operation system for which C was designed. And based on this, for this writability, we have some important characteristics that influences this writability. They are simplicity and orthogonality. If a language has a large number of different constructs, some programmers might not be familiar with all of them. Okay, so this situation can lead to a misuse of some features and a disuse of others that may be either more elegant or more efficient or both. Okay, than those that are used. And it may even be possible to use unknown features accidentally with the bizarre results. So therefore, a smaller number of primitive constructs and a consistent set of rules for combining them, that is orthogonality, is much better than simply having a large number of primitives. Okay, so that is the ideal thing. So we need to have a smaller number of primitive constructs and a consistent set of rules for combining them. Okay, that is much better than simply having a large number of primitives. Okay, so programmer can design a solution to a complex problem after learning only a simple set of primitive constructs. And what we said earlier, as we said earlier, too much orthogonality can be a detriment to writability. So that is, errors in programs can go undetected when nearly any combination of primitives is legal. Okay, so when any combination of primitives is legal, sometimes we will not be able to detect some errors. So this can lead to code absurdities that cannot be discovered by the compiler. And we have the support for abstraction. That is, abstraction means the ability to define and then use complicated structures or operations in ways that allow many of the details to be ignored. Okay, so we'll be hiding most of the details. So abstraction is a key concept in contemporary programming language design. And this is actually a reflection of the central role that abstraction plays in modern programming language methodologies. So the degree of abstraction allowed by a programming language and the naturalness of its expression, okay, are therefore important to its writability. Programming languages can support two distinct categories of abstraction, it is process and data. Process abstraction data. So a simple example for this process abstraction is the use of a subprogram to implement a sort algorithm that is required several times in a program. Okay, so suppose a program needs sorting multiple times, so we'll use a sorting subprogram that can be used multiple times. Okay, that is a process abstraction. So without the subprogram, the sort code would need to be replicated in all these places where it was needed. Okay, which would make the programmer much longer and more tedious to write the code. So perhaps more important, if the subprograms were not used, the code that used the sort program, sort subprogram would be cluttered with the sort algorithm details and greatly obscure in the flow and overall intent of that code. Okay, that is the problem with this if we are using this code again and again, but rather we can use a sort subprogram and that can be used everywhere that is needed. And for example, as a data abstraction, consider a binary tree that stores integer data in its nodes. Okay. Such a binary tree would usually be implemented in a language that does not support pointers and dynamic storage management with a heap. For example, like Fortran. As three parallel integer arrays where two of the integers are used as subscripts to specify of offspring nodes. And we know in C++ and Java, these trees can be implemented by using an abstraction of a tree node in the form of a simple class with two pointers. Pointers means references and an integer. And the latter representation makes it much easier to write a program that uses binary trees in these languages than to write one in Fortran 77. Okay, and we want to have code for these binary trees. If we are using it for Fortran 77, we need to use three parallel integer arrays, and two of these integers are used as subscripts to specify this offspring nodes. Okay, so that is a problem with the Fortran. So suppose we have binary trees, all this, then if we go with this Java or C++ representation, that will be much easier. And the overall support for abstraction is clearly an important factor in the writability of languages. Then the third point is expressivity. So expressivity in a language can refer to several different characteristics. For example, in languages such as APL, it means that there are very powerful operations that allow a great deal of computation to be accomplished with a very small program. Okay, so with a very small program, we'll be able to allow a great deal of computations to be accomplished. More commonly, it means that a language has relatively convenient ways of specifying computations. For example, in C++ or in C, the notation count plus plus is more convenient and shorter than count is equal to count plus 1. Okay, so that is expressivity. Also, the and then Boolean operator in ADA is a convenient way of specifying short circuit evaluation of a Boolean expression. So, we will be studying about short circuit evaluation in second module. So, the inclusion of the for statement in Java makes writing counting loops easier than with the use of while. Okay, if we are using for, that is very convenient for writing counting loops. Okay, and that is also possible with while loops, but easier will be if you are using for. And if we notice or if you focus on these things, then all this increase writability of a language. And third point is about the reliability. A program is said to be reliable Okay, if it performs to its specifications under all conditions. Okay, that is meant by a reliable code. A program is said to be reliable if it performs to its specifications under all conditions. So it should stick to its specification. So we have different features that have significant effect on the reliability of programs in a given language. The first feature is about type checking, and type checking is simply testing for type errors in a given program, either by the compiler or during the program execution. That is very important. And type checking is an important factor in language reliability because runtime type checking is very expensive. Compile time type checking is more desirable. Usually we do this type checking during compilation. So furthermore, the earlier errors in programs are detected, the less expensive it is to make the required repairs. Okay. So when we perform this type checking during compilation, so we'll detect the errors earlier. Okay. So that will make it less expensive to make repairs on this program. So the design of Java requires checks of the types of nearly all variables and expressions at compile time. And this virtually eliminates type errors at runtime in Java programs. And we'll discuss more about type checking in later modules. And one example of how failure to type check at either compile time or runtime has led to countless program errors is the use of subprogram parameters in the original C language. It is in this language the type of an actual parameter in a function call was not checked to determine whether its type matched that of the corresponding formal parameter in the function. For example, an int type variable could be used as an actual parameter in a call to a function that expected a float type as its formal parameter. So we are supplying int and formal parameter is float, and neither the compile nor the runtime system would detect the inconsistency. Okay, and for example, because a bit string that represents the integer 23 is essentially unrelated to the bit string that represents a floating point 23. Okay, integer and a floating point are different. If an integer 23 is sent to a function that expects a floating point parameter, what happens? Any uses of the parameter in the function will produce nonsense. Okay, because the internal representation for integer and floating point are different. So such problems are often actually difficult to diagnose. Okay. So the current version of C has eliminated this problem by requiring all parameters to be type checked. So before running the program during compilation time itself, all the parameters will be type checked so that this kind of problem will not arise. And we have exception handling. So the ability of a program to intercept runtime errors. Okay, take corrective measures and then continue is an obvious aid to reliability. Okay, so that is we'll intercept runtime errors, then we'll take corrective measures and then continue. Okay, that is known as exception handling. So this language facility is called exception handling. ADA, C++, Java and C# include extensive capabilities for exception handling. And such facilities, that is exception handling facilities, are practically non-existent in many widely used languages, including Fortran, C. And we'll be studying about exception handling later. Then we have aliasing, that is the third point to reliability. So aliasing is having two or more distinct names that can be used to access the same memory cell. We have one memory cell and we have two names to access that. Okay, it is now widely accepted that aliasing is a dangerous feature in a programming language. Most programming languages allow some kind of aliasing. For example, two pointers set to point to the same variable, which is possible in most languages. In such a program, the programmer must always remember that changing the value pointed to by one of the one of the two changes the value referenced by the other. Okay, that should be made. Then only these two values or these two variables become consistent or reliable. In some languages, aliasing is used to overcome deficiencies in the language's data abstraction facilities. And other languages greatly restrict aliasing to increase their reliability. And the fourth one is readability and writability. So both readability and writability influence reliability. A program written in a language that does not support natural ways to express the required algorithms will necessarily use unnatural approaches. Unnatural approaches are less likely to be correct for all possible situations. So easier a program is to write, the more likely it is to be correct. Okay. So the readability and the writability is a major concern, and that readability affects reliability in both the writing and maintenance phases of the life cycle. So programs that are difficult to read are difficult both to write and to modify. Okay, if it is very difficult to read, then of course it is difficult to write or modify. And the last criteria is about cost. So the total cost of a programming language is a function of many of its characteristics. For example, the first characteristic is there is the cost of training programmers to use the language, which is a function of the simplicity and orthogonality of the language and the experience of the programmers. Although more powerful languages are not necessarily more difficult to learn, they often are. Okay, so the first cost is for training programmers. If the program is very simple and orthogonality is there, all these factors actually, this cost of training is a function of simplicity and orthogonality. Okay, and also the experience of the programmer. If the programmer is very experienced, he will be easily learning all these concepts. And second thing is there is the cost of writing programs in a language. This is a function of the writability of the language. Okay, writing programs in the language. So which depends in part on its closeness in purpose to the particular application. So if it is close to a particular application or particular program domain, that will be used. Okay, so the original efforts to design and implement high-level languages were driven by the desire to lower the cost of creating software. And both the cost of training programmers and the cost of writing programs in language can be significantly reduced in a good programming environment. Okay. So third factor is there is the cost of compiling programs in the language. Okay. So a major impediment to the early use of ADA was the prohibitively high cost of running the first generation ADA compilers. Okay, during the times of ADA, running cost of this ADA compilers was very high, and this problem was diminished by the appearance of improved ADA compilers. And fourth point is the cost of executing programs written in a language is greatly influenced by that language design. A language that requires many runtime type checks will prohibit fast code execution regardless of the quality of the compiler. So although execution efficiency was the foremost concern in the design of early languages, it is now considered to be less important. And a simple trade-off can be made between compilation cost and execution speed of the compiled code. That is by using optimization. And optimization is the name given to collection of techniques that compilers may use to decrease the size or increase the execution speed of the code. So we have a compiled code, and after that this code will be optimized. Optimized means we'll be reducing size of this code, or sometimes we will be in effect we will be fasting or speeding up the execution, okay, of the code that is produced by the compiler. And we have most of the intelligent compilers that perform high level or most sophisticated of optimization techniques. Okay, and the fifth factor in the cost of a language is cost of the language implementation system. And one of the factors that explains the rapid acceptance of Java is that free compiler and interpreter systems became available for it soon after its design was released. And a language whose implementation system is either expensive or runs only on expensive hardware will have a much smaller chance of becoming widely used. Okay, if its implementation system is very expensive or if it runs on expensive hardware, then people will be reluctant to use all this programming language. So for example, a high cost of first generation ADA compilers helped prevent ADA from becoming popular in its early days. Okay, so when ADA was implemented, it has a high cost of this ADA compilers. That's what we discussed. And sixth point is that there is the cost of poor reliability. If the software fails in a critical system such as a nuclear power plant or an X-ray machine for medical use, the cost could be very high. Okay, so the failures of non-critical systems can also be very expensive in terms of lost future business or lawsuits over defective software systems. Okay, and we know if the system performs or system fails in critical systems like nuclear power plants, there it should not fail. Okay, or if it is used for medical purposes, the failure cost very high. Okay, and in some cases in non-critical systems also the failures are not acceptable and they are very expensive, because if we do or if we develop some softwares for some clients, and if it makes or if it fails for some applications, what will happen? We'll lose our clients. Okay, or we may be or we'll be forced to face some uh, punishments or some problems. Okay, and the final consideration is the cost of maintaining programs. Okay, so which includes both corrections and modifications to add new functionality. The cost of software maintenance depends on a number of language characteristics, primarily readability. Okay, maintenance cost depends on readability because maintenance is often done by individuals other than the original author of the software. Okay, so poor readability can make the task extremely challenging. And the importance of software maintainability cannot be overstated. It has been estimated that for large software systems with relatively long lifetimes, maintenance costs can be as high as 2 to 4 times as much as development costs. Okay, maintenance cost is always very high compared to the development cost. And we can use a number of other criteria that is used for evaluating programming languages. One is portability. Okay, so what is meant by portability? The ease with which programs can be moved from one implementation to another. And portability is most strongly influenced by the degree of standardization of the language. Some languages such as BASIC are not standardized at all, making programs in these languages very difficult to move from one implementation to another. And standardization is a time consuming and difficult process. Okay, and we have generality, that is the applicability to a wide range of applications, and well definedness are two other criteria. So generality means the applicability to a wide range of applications, and well definedness is the completeness and precision of the language official defining document. Okay, and most criteria, there's readability, writability, and then reliability are neither precisely defined nor exactly measurable. They are useful concepts and they provide valuable insight into the design and evaluation of programming languages. And we can have or the language design criteria are weighed differently from different perspectives. And language implementers are concerned primarily with the difficulty of implementing the constructs and features of the language. Okay, language implementers has only this problem, difficulty of implementing the constructs and features. Language users are worried about writability first and readability later. And language designers are likely to emphasize elegance and the ability to attract widespread use. And we know these characteristics often conflict with one another. Okay, so these are the main language evaluation criteria. Okay, thank you.